This is Honors Geometry, Section 10.2 Notes, talking about the law of sines. Law of sines. Let triangle ABC be any triangle with A, B, and C representing the measures of sides opposite angles with measures A, B, and C respectively. Respectively means in the same order. A was first, B was second, B was second, C was third, C was third. So let's draw this triangle. It can be any type of triangle, it really doesn't matter what it is. Let's say that the angles are A, B, and C. Opposite A is the same letter but lowercase, same with B, same with C. According to the law of sines, if you have any triangle, if you take sine of an angle over its opposite side, which is what this is saying, that's going to be the same ratio if you take sine of a different angle over its opposite side, and that will be the same ratio as sine of the third angle over its opposite side. Now in practice, you won't have an equation with two equal signs. You're either going to have these two equal to each other, or these two, or the first and the last. You're not going to use all three at the same time. So that's what law of sines is. What this enables us to do is to solve triangles that aren't right triangles. Up to this point, we had to have right triangles. So when can you use law of sines? I don't know how this got misnumbered. This should be a 1 and a 2. If you're given the measure of two angles in any side of the triangle, or you're given the measure of two sides in an angle opposite one of those sides. So the first scenario, two angles and any side. Keep in mind, if you know two angles, you can figure out the third. Other scenario, you're given two sides and an angle opposite one of those sides. In either case, you can use law of sines if you know an angle and the side opposite that angle. Definition: solving a triangle, find the measure of all the angles and sides of a triangle. Well, something you got to be careful about. This is angle side side. Now we learned earlier, talking about congruency of triangles, if I give you an angle and then two sides, so the angle is not included in the two sides, we don't necessarily know which triangle we're talking about. That is not a congruence test. So what we need to be really careful about is called the ambiguous case of sines. And this ambiguous case of sines happens when you're given angle side side. Let me attempt to explain this to you. Let's say that we are given triangle ABC, and we're told the measure of angle A is, I don't know, 30 degrees. And let's say that side B is 5. And side C is, I don't know, 3. So let me show you why this doesn't work. So here is side I think I might have did that wrong. I'll tell you what, I'll get into that in a second, what those were. So let's say that this is A, and we know that this is 30 degrees. And let's say that we're told, let's say that B is someplace on this ray. We don't know where it is. Let's say that C is definitely here. That's locked in. So in that case, let's say that we know B is 10. And then let's say that A is 7. So here's how this works. This is why the ambiguous case of signs exists. I'm going to draw a circle with C at the center. So let's say that's a circle with C at the center. And why am I drawing a circle? Just to show that the distance from C to the circle is the same on both sides. Now let's say that was 7, like I said. This is not to scale. But the point is, A could be 7 and A could be 7. And what that does for the triangle, so first of all, we're given angle, side, side, or angle, side, side. Because this could be two different triangles. It could be this triangle right here, or with the same measurements of 30, 10, and 7, it could be this triangle. Hopefully you can see those are two completely different triangles. The point I'm trying to make, and I don't think I'm doing a very good job of it, is if you're given an angle, such as 30 degrees, and a side, and another side, angle, side, side, it's possible that two different triangles could fit that description. That's why it's called the ambiguous case of signs. Now I'm going to try to avoid giving you that scenario here in geometry, because that's a lot to handle. But in pre-calculus, we will do this. I just want you to be aware of it. So if something weird happens, if you give an angle, side, side, basically we should expect it. We should expect something weird to happen. But I'm pretty sure I won't give you angle, side, side in any of the problems. All right. So long story short, we're going to do this in pre-calculus. All right, let's get to an actual problem. So I think I might have freaked you out there. My apologies. For the following examples, round sides to the nearest tenth, angles to the nearest whole number. Solve triangle ABC. That means find all the missing measurements. So I'm going to draw triangle ABC. Opposite the angles is the same letters, but lowercase. It says the measure of angle A is 50 degrees. Measure of angle B is 67 degrees. Side B is 10. First thing you want to ask yourself is, self, can I use law of sines for this? You can, because you have an angle and the side opposite of it. We're going to find side A first because we know what angle A is. So we could write the following. I'll tell you what, before we do that, let's go a little simpler. Let's find measure of angle C. We could easily find that. That's the angle addition, or the angle sum theorem that we learned a long time ago. Measure of angle C plus 50 degrees plus 67 degrees is 180 degrees. So the measure of angle C plus 117 degrees is 180. Measure of angle C is 63 degrees. So this is 63. It's not rounded, so we can use that to find answers. Using a law of sines, what we're focusing on is our new lesson here. We're going to take sine of an angle, 67 degrees, over its opposite side, 10. I suggest when you write your first ratio, you write it using numbers only. In this green ratios, you're only going to write initially using numbers because we have the angle on the side opposite of it. According to the law of sines, that should be equal to sine of 50 degrees over its opposite side, which is side A. Now it's algebra. We're trying to solve this for A. I'm going to multiply both sides by 10 and A to get rid of my fractions. On the left, the 10's cancel. On the right, the A's cancel. So on the left, I'm going to get A times sine of 67 degrees equals 10 times sine of 50 degrees. It's really important that when you're multiplying a number times a trig function that you're writing it on the left side. Now to get a by itself, I'm going to divide both sides by sine of 67 degrees. A is going to be 10 sine of 50 degrees over sine of 67 degrees. This is all one object. This is all one object. Nothing cancels there. If you put this in your calculator, you're going to find that A is about 8.3. Please put that in your calculator and confirm that you're getting that. So we know that's 8.3. That's a rounded number. We want to avoid using that to find other answers. Let's make another equation to figure out what side C is. Sine of 67 degrees over its opposite side of 10 should be equal to, that's the original ratio that I used, sine of 63 degrees over its opposite side of C. Notice how similar this equation is to this equation. Extremely similar. Law of sines. I'm going to multiply both sides by 10 and C to get rid of my fractions. On the left, I'm going to get C times sine of 67 degrees. On the right, I'm going to get 10 times sine of 63 degrees. To get C by itself, divide both sides by sine of 67 degrees. I put this into my calculator, I would get about 9.7. Put that in my picture, and I just want to examine to see if my picture makes sense. Opposite the smallest angle should be the smallest side. Opposite the biggest angle should be the biggest side. Opposite the middlest angle should be the middlest side. That all checks out, so my answer at the very least is reasonable. Excuse me, is reasonable. A tickle in my throat. Ain't that something? A tickle in my throat. Same directions for number 2. Draw a triangle. Any random triangle. That's not a triangle. Call the angles A, B, and C. Call the sides opposite A, B, and C, but lowercase. We're told little a is 10. Big C is 124. Little c is 25. Find the measure of angle A. Using the law of sines. Now, this is one of those cases where this is the ambiguous case of sines. And there's different rules for that. Once again, I said I wouldn't do this to you, and this ends up working out just fine. And that's because the angle we're given is obtuse. If the angle you're given is obtuse, 124 is obtuse, there is no ambiguous case of sines in this case. It's just going to work out. So to find the measure of angle A, first we want to ask ourselves, can we use law of sines? The answer is yes, because we have an angle and the side opposite of it. So sine of 124 degrees, it's an ugly 2, over its opposite side should equal sine, of an angle, in this case it's the measure of angle A, over its opposite side, which is 10. Now, like on the previous problem, don't write this down. I multiplied both sides by 25 and 10 to get rid of my fractions. The reason I don't need to do that for this one is I'm trying to get A by itself. The left side doesn't have any variable in it. Just leave the left side alone. I want to get this fellow by itself, so I'm going to multiply both sides by 10 initially. On the left, I get 10 times sine of 124 degrees over 25. On the right, I get sine of the measure of angle A, because the 10s cancel on the right. Now, it's true that you could simplify 10 over 25 don't bother with it. Trying to get measure of angle A by itself. It is attached to sine by sine. To unattach it, I'm going to do sine inverse to both the left and right side of the equation. On the right, the sine and the sine inverse cancel. On the left, we have a bit of a calculator monster. So please put this in your calculator to confirm that you're putting it in correctly. You would find to the nearest degree, this is about 19 degrees. Which seems reasonable since the smallest side, 10, is much smaller than 25, and the biggest angle is 124. It's all good. In the hood, let's try this last one. Two of George's paradoxosaurs, Bert and Ernie, fly away from George at the same time. Both paradoxosaurs travel at a speed of 50 miles per hour. Bert flies in the direction of 50 degrees west of north, while Ernie travels 10 degrees west of south. How far apart are Bert and Ernie after 4 hours? This is a tough one. Let's start by saying this is where George is. It says both paradoxosaurs travel at a speed of 50 miles per hour. That's important, but I don't know how to use it yet. Bert flies in the direction of 50 degrees west of north. Now, it's likely that you've never seen something like this before. Let me draw a compass rose. Let's call this north, east, south, and west. If Bert is flying 50 degrees west of north, the of north means you're starting in the north direction. So let's say that this is in the north direction, going in the direction of west. We're going west of that. So the angle is formed here. That means this angle here is 50 degrees. This is where Bert is. Ernie travels 10 degrees west of south. So you start at south and you go in the direction of west. This is a naming convention for angles that is used in the real world. That is where Ernie is. How far apart are Bert and Ernie after 4 hours? So to finish our triangle, I'll just call this little g. We're trying to figure out what little g is. Excuse me. You'll notice in our triangle we don't have the lengths of anything. That's not good. Hopefully you know that the distance someone travels is equal to their rate times their time. The distance that Bert and Ernie are going to go, it says both of their rates are 50 miles per hour, and they're both traveling for 4 hours. That means that after 4 hours, they will have gone a total distance of 200 miles apiece. So this is 200, and this is 200. Oh, what kind of triangle does that make that? It makes this isosceles, which means these angles have to be the same. That's the isosceles triangle theorem. What's the measure of this angle here? Angle BGE. Well, I think you'll recognize that if we take 50 plus this angle we're missing, plus 10, those added together should be 180 because it makes a straight angle. So the measure of angle BGE plus 50 degrees plus 10 degrees, that should be 180. It's going to be the measure of angle BGE plus 60 is 180, which makes the measure of angle BGE 120 degrees. I can put that in my picture. That's 120. What about these other angles? Well, we said it's an isosceles triangle, so the base angles are the same. So for example, the measure of angle B plus the measure of angle B, because B and E are the same, plus 120 should be 180. That means 2 times the measure of angle B should be 60. That makes the measure of angle B have to be 30. So these are each 30. We are using lots of information that we've learned this year for this problem. So where does that leave us? We're trying to figure out what G is. We can use the law of sines. We could say, so I drew this picture. I got so many steps here. I drew this picture. I found the distance they traveled, figured out the measure of angle BGE, figured out the measure of angle B and E. Now step 4, if I take sine of 30 degrees over its opposite side of 200, that should be equal to sine of 120 degrees over its opposite side of little g. Little g is my rapper name, by the way. They call me little g. I'm going to multiply both sides by g and 200. Trying to make this simpler for myself. And I'm going to divide both sides by sine of 30 degrees. I put that into my calculator. The directions said, how far apart are they? It doesn't say what to round to. I'm just going to round to the nearest whole number since it didn't tell me. I got 346 for this. Word problem deserves a sentence answer. Bert and Ernie are about 346 miles apart. That concludes the notes. Please do the homework. Thank you very much.